The HVACR service technician uses an array of tools and test instruments to diagnose problems and evaluate system performance. One tool that is readily available, inexpensive, and yet rarely used to its fullest advantage is the pressure temperature card, or PT card.
In this training video, we are going to review the principles of the pressure-temperature relationship in an operating system. Once you understand the basics, you'll be able to use either the traditional PT card or our ChillMaster app as an ideal service tool.
The pressure-temperature relationship, as shown in the PT card, is simply a chart listing the boiling temperatures of the refrigerant. By convention, a PT card has pressures listed on the left side of the chart and the corresponding boiling temperatures for each of the listed refrigerants on the right. Refrigerant at these conditions is referred to as saturated. Saturated refrigerant can be 100% vapor, a mixture of liquid and vapor, or 100% liquid. At temperatures above saturation, the refrigerant becomes superheated vapor. At temperatures below saturation, the refrigerant becomes subcooled liquid. Saturated refrigerant must exist in two places of a normal operating system: in the evaporator and in the condenser. This is due to the fact that the refrigerant becomes a liquid and vapor mixture in the evaporator and condenser. Anytime you have a liquid and vapor refrigerant mixture, the refrigerant will be at saturation. For systems with a receiver, saturated refrigerant will also be found at the liquid-vapor interface at the refrigerant level in the receiver. For our example, we will use R134A. If we measure the pressure of the refrigerant, we can easily determine its saturation temperature. This is true anywhere in the system, not just the evaporator, condenser, and receiver. At points in the system where only vapor is present, the actual vapor temperature will be at or above the temperature indicated on the PT card. Vapor will only be present in the suction and discharge lines with a normally operating system. Where we have only liquid present, the actual liquid temperature will be at or below the temperature indicated on the PT card. Liquid refrigerant will be present in the liquid line which connects the condenser and evaporator coils.
Now that we understand the basic principles of the PT relationship, let's start to analyze a system for superheated, subcooled, and saturated conditions.
This system diagram shows some actual pressure-temperature measurements of a normally operating system using refrigerant 134A. This will give a better understanding of the condition of the refrigerant at the various points. The measured pressure at the evaporator coil outlet is 18 psig. Assuming there is minimal pressure drop in the evaporator coil, we will have an 18 psig pressure in the coil. 18 psig on the PT card indicates a temperature of 19 degrees Fahrenheit. Because liquid and vapor must be present in the evaporator coil, we must have 19 degree Fahrenheit refrigerant in the coil. If we were able to place a thermocouple on the coil surface where the refrigerant was evaporating, it should reveal this temperature. If 19 degrees Fahrenheit is measured at the evaporator coil outlet, we know the refrigerant is still saturated, and we likely have a liquid and vapor refrigerant mixture entering the suction line. However, our actual measured temperature in this case is 27 degrees Fahrenheit. Because this temperature is higher than our saturated temperature, we know the refrigerant at this point is superheated vapor. To determine the amount of superheat in the vapor, simply take the difference between the measured temperature and the saturated temperature indicated by the PT card. In this case, the difference between 27 degrees Fahrenheit and 19 degrees Fahrenheit is 8 degrees Fahrenheit superheat. As a second example, let's take readings at the compressor inlet. Our pressure gauge reads 16 psi. Our measured temperature is 47 degrees Fahrenheit. To calculate our superheat, we again reference our PT card. 16 psig on the PT card indicates a temperature of 16 degrees Fahrenheit. The difference between 47 degrees Fahrenheit measured temperature and 16 degrees Fahrenheit from the card is 31 degrees Fahrenheit superheat. At points in the system where liquid is present, the actual liquid temperature will be at or below the temperature indicated on the PT card. Liquid will be present in the liquid line, which connects the condenser and evaporator coils. Let's examine the gauge we have installed at the outlet of the condenser coil. The measured pressure is 155 psig. Assuming there is minimal pressure drop in the condenser coil, we will have a 155 psig pressure in the coil. 155 psig on the PT card indicates a temperature of 114 degrees Fahrenheit. Because liquid and vapor must be present in the condenser coil, we must have a 114 degree Fahrenheit refrigerant in the coil. If we were able to place a thermocouple on the coil surface where the refrigerant was condensing, it should reveal this temperature. If 114 degrees Fahrenheit is measured at the condenser coil outlet, we know the refrigerant is still saturated, and we likely have a liquid and vapor refrigerant mixture entering the liquid line. However, our actual measured temperature in this case is 105 degrees Fahrenheit. Because this temperature is lower than our saturated temperature, we know the refrigerant at this point is subcooled liquid. To determine the amount of subcooling, simply take the difference between the measured temperature and the saturated temperature indicated by the PT card. In this case, the difference between 114 degrees Fahrenheit and 105 degrees Fahrenheit is 9 degrees Fahrenheit. With most systems, one can expect to find the refrigerant in the liquid line to have some amount of subcooling. In particular, systems employing a TEV should have subcooled refrigerant liquid entering the valve. When a system employs a liquid receiver, we will find saturated refrigerant at the liquid-vapor interface in the receiver. If the measured pressure in the receiver is 155 psig, we know the temperature at the refrigerant level to be 114 degrees Fahrenheit. The fact that saturated refrigerant exists in the receiver is at times a source of confusion and does not mean subcooled liquid cannot exist in a receiver. If the condenser provides subcooled liquid to the receiver, subcooled liquid will be present in the receiver also. Only the liquid-vapor interface in the receiver must be at saturation. As another example, let's take readings at the TEV inlet. Our pressure gauge reads 150 psig, and our measured temperature is 104 degrees Fahrenheit. To calculate our subcooling, we again reference our PT card. 150 psig on the PT card indicates a temperature of 112 degrees Fahrenheit. The difference between 112 degrees Fahrenheit and 104 degrees Fahrenheit is 8 degrees Fahrenheit. With the PT card, we should be able to determine the condition of the refrigerant at any point in the system by remembering the following rules. Rule 1. If we have a liquid and vapor mixture present, as we do in the evaporator and condenser, we have saturated refrigerant, which will correspond to our PT card. Rule 2. We have superheated vapor when our measured temperature is greater than the saturation temperature indicated by our PT card. The amount of superheat will be the difference in these two temperatures. Superheated vapor will be present in the suction and discharge lines of a normally operating system. Rule 3. We have subcooled liquid when our measured temperature is less than the saturation temperature indicated by our PT card. The amount of subcooling will be the difference in these two temperatures. Subcooled liquid will only be present in the liquid line, which connects the condenser and evaporator coils of a normally operating system. Understanding the refrigerant pressure-temperature relationship in the various parts of a system will help identify and pinpoint problem areas. Because the values at the inlet of the compressor indicate a saturated condition, we know we have a problem. In this case, we have floodback, because in the suction line, the refrigerant should only exist as a vapor.
So far in our example, we have been evaluating temperatures and pressures in an ideal type of system. Unfortunately, most systems do not typically have pressure taps located immediately after the condenser or evaporator coil. Oftentimes, we are forced to make assumptions and estimate the operating pressures.
It is often difficult to measure pressure at the outlet of the condenser coil. As a result, the pressure must be taken at the compressor discharge service valve. To determine the pressure at the outlet of the condenser, one must estimate the pressure loss in the discharge line and condenser coil and subtract this value from the pressure reading. Only by installing a pressure tap at the outlet of the condenser can we eliminate guesswork. It is often difficult to measure pressure at the outlet of the evaporator coil. As a result, the pressure must be taken at the compressor suction service valve. Then, to determine the pressure at the outlet of the evaporator, one must estimate the pressure loss in the suction line. Add this value to the pressure reading. This value could easily vary from 0.5 to 4 psi with properly designed systems, depending on the type of system and length of suction line. To eliminate guesswork and be as precise as possible measuring superheat, a pressure tap near the TEV sensing bulb location must be installed.
So let's recap. There are three basic rules for determining the refrigerant condition in an operating system.
Rule 1. When we have refrigerant liquid and vapor existing together, we have saturated refrigerant, and the pressure and temperature will correspond to our PT card. Rule 2. If our measured temperature is above the saturated temperature indicated on our PT card, we must have superheated vapor. The amount of superheat is the difference between our measured temperature and the saturated temperature. Rule 3. If our measured temperature is below the saturated temperature indicated on our PT card, we must have subcooled liquid. The amount of subcooling is the difference between our measured temperature and the saturated temperature.
Understanding these rules and knowing where these three conditions can occur will enable you to use the PT card or the ChillMaster app as a vital tool in diagnosing system problems.